Welcome to Chemical Process Safety. This video is about Pasquill-Gifford dispersion models. In the last video, I mentioned that there are multiple types of dispersion models, and unfortunately, a lot of them are theoretically useful, but they are difficult to apply. And that is because the concept of eddy diffusivity, which is something that you might have learned about in your fluids class. So just imagining what a hazardous chemical that is dispersing in the atmosphere, there are tons of variables at play here. And the eddy diffusivity kind of quantifies the degree of mixing. But as you can imagine, that is difficult to quantify in and of itself. And this is a key parameter in a lot of the dispersion models. And for that reason, because it's difficult to measure, it isn't that useful in practice. In contrast, the Pasquill-Gifford model is easy to apply in practice because it doesn't make use of the eddy diffusivity. Instead, it defines something called a dispersion coefficient, which is given the variable sigma x, sigma y, and sigma z, and we'll talk about that as this video goes on. The key assumption here is that sigma x is equal to sigma y, and x, y, and z directions are as normal. So x is along the direction of the wind, y is the crosswind, and then z is vertical up and down. So let's get started with discussing some of the ways that you would use the Pasquill-Gifford model to problem solve. The first step that you'll have to do is define the atmospheric stability. This is one of the variables that I mentioned in the last video. And although the word stable, you might think that it is a good thing in the context of process safety, stability in terms of atmospheric stability is actually bad. And that is because the more stable the atmosphere is, the less mixing that there is. And in general, mixing and turbulence will break up a cloud of hazardous toxicant and disperse it quickly. The atmospheric stability is a function of sunlight and wind speed. The book uses the word insolation, which I had never heard that word before I read it, so I looked it up and I learned a new one. And we'll assign each condition a letter from A to F. We'll see that in table 5.1 in just a second. Strong insolation is defined in the footnote to be a sunny afternoon in England, because I think the authors of this model were British. So that means in Florida, what we would call, medium insolation is probably strong. So keep that in mind. Let's look at the table. So once again, here you see that it is a function of the daytime insolation or the sunlight and the surface wind speed. So each one is given a letter from A, which is extremely unstable. So again, A is good and F is bad. So what you can see is in the daytime, the letters A, B, and C indicate that we have extremely unstable or slightly unstable, indicating good mixing. Whereas in nighttime, we've got D, E, and F, which correspond to stable and relatively little mixing. A couple of things to mention here, or just to note trend-wise. As the daytime insolation goes up, so as it gets sunnier and sunnier, that is going to make the atmosphere more and more unstable. So you see this for low wind speeds and you see it for high wind speeds. So for example, here we're going from B to A, there we're going from D to C. That makes perfect intuitive sense, right? The more the sun is beating down on the ground, the warmer that the air is going to be on the ground and the more it's going to want to rise. So no surprises there. One thing that is slightly more confusing at first glance is that as the wind speed increases, generally we become less stable. And the reason for that is as the wind speed increases, there's less vertical mixing, if you will, if the wind speed is horizontal, right? So if there is speed going in the X and Y directions, there would be necessarily less in the Z direction. However, that is a trend that you will only see in daytime. So for example, for strong insolation, we're going from A, which remember is extremely unstable, to C, which is slightly unstable. So we are increasing stability. In contrast, at nighttime, we're going from extremely stable to slightly less stable. So the trend kind of reverses. And again, if you think about that for just a second, I think it should make sense because there's very little vertical mixing at nighttime to begin with. So I wrote that here in a note as well. Okay, step 2 is deciding to model the release as a puff or a plume. Recall that in the first video, puff is an instantaneous release. And again, we're stretching the definition of that word to mean up to 10 minutes. Plume is a release that occurs over a time scale of 10 minutes or greater. You would then calculate the corresponding dispersion coefficients sigma y and sigma z using table 5.3 for puffs and 5.2 for plumes. Let's take a look at what those tables look like. And here we are. I've cropped out the titles of the tables, but the one on the top is for a plume, so that's a continuous release, and the one on the bottom is for a puff or an instantaneous release. Things to mention here is that the atmospheric stability, whatever you have decided, would be one of the inputs. And then the other input is the x variable. And x is defined to be the distance in meters away from the release. So for example, if you are interested in what the downwind concentration will be 1,000 meters in the direction of the wind, you would plug in 1,000 for x. That's pretty much it. You would just, this is plug and chug. You decide what the atmospheric stability is. Oh, and also rural versus urban is different. And what you'll see here is that urban is going to increase the mixing. So the dispersion would in general be greater. So this is a way that you would calculate what your dispersion coefficients are, and then that would factor into the next step. I'll also quickly mention the puff table as well. Sorry, this is the puff table. This is just a function of the x distance and the atmospheric stability. It's not different for urban versus rural. All right, step 3 is define the appropriate model in section 5.2. This is going to depend on whether it's a puff versus a plume, the height of the release, and the desired coordinate system. So whether or not you are fixing your coordinate system, or if you're talking about a puff, the alternative is that the coordinate system moves with the puff. So the equations here they look pretty intimidating, quite honestly. Honestly, most of it, well, that's not true. This is the most general version. I was going to say most of it cancels. It cancels in certain conditions. So for example, if you are only interested in the concentration directly downwind, you would, for example, set the y coordinate equal to 0. I think I forgot, actually. I didn't have that on this page of notes, but the coordinate system is the origin, x equals y equals z equals 0 for a fixed coordinate system is where the release occurs. And then x, as I mentioned, is the distance in the direct wind direction. So this is not oriented with a compass, for example. If the wind is pointing northwest, then x is oriented to be in that exact wind direction. Y is exactly perpendicular to that, the crosswind direction in meters, and then z is the vertical distance up or down. So if elevation changes, for example, you'd have a z. But that's another important thing of what I was mentioning is oftentimes you're going to have things that are canceling. So if the release occurs at ground level and you're interested in the ground level concentration, because that would be where people would be living, then Z would cancel and you wouldn't have to worry about it. One other thing to mention is that the sigma X and the sigma Y, again, are exactly identical. I don't know why they distinguish. I think it just serves to confuse more than anything, but I have never encountered a situation where sigma X was different than sigma Y, at least in the Pasquill-Gifford system. For a puff, if you are focusing on the coordinates moving with the center of the cloud, then the x coordinate is always u, the wind velocity, times t. So this is just another example of what one of these dispersion models may look like. The other parameters that you might need to know are QM or QM star. So the star means this is an instantaneous amount released. QM can come from a source model or it could be given by the problem statement. And then QM without a star is the rate of continuous release. Other than that, I think those are the only other parameters that I haven't explained. I've explained everything else. So pi is just the number 3.14. The dispersion coefficients we've already gotten. U is the wind velocity. T is the time. So this is for a puff, but a plume would be somewhat different. Let's look at one for the plume. Okay, here is a plume model. This one is for a continuous steady state source. So that just means a plume at a height h sub r. So for example, if it was a smokestack and the release was occurring out of that and it was 50 meters in the air, HR would be equal to 50. And again, it's just plug and chug. After you find the right dispersion model that describes your situation, it's plugging into the equation and then solving for the concentration. Let's finish this video by talking about some notes and limitations of the Pasquill-Gifford model. First one is that for a plume, the concentration is always highest at the release point. That's going to make intuitive sense, right? The concentration here is going to be greatest, and then as it disperses, the word dispersion kind of implies that the concentration is decreasing as it goes. If the release is at a height, the highest ground level concentration is going to be downwind. So imagine that this is a very tall stack. Again, the closer you are paradoxically to that release, the safer you're going to be, because it takes some time for the toxicant to disperse itself down to ground level. Second note is that for a puff, the max concentration is always at the center of the puff, wherever that is moving. The max ground level concentration is always directly below the puff. It's kind of difficult to visualize, but once you do visualize it, I think it's easy to see. A puff is going to be moving at the same time that it's dispersing. So wherever that puff moves, the direct center of that is always going to be the highest concentration. And that's related to the same idea for the plume being the highest concentration right at the very beginning. Third point is that there is a ton of uncertainty with these models. And again, these are just estimates. So I mentioned at the end of last video, it's always better to be conservative and err on the side of caution. So for example, if you're stuck between atmospheric stability of D and E, for example, it would be better to assume E, because that way the concentration is always going to be less than what you predict. So that is, any type of error is not good, right? Obviously, we'd prefer to be exact and precise, but if you're going to be wrong one way or the other, it's better to be wrong in the way that maximizes caution. And as always, I like to harp on this point all the time, imperative always in engineering to state your assumptions. It does me absolutely no good to simply say, oh, the concentration at this point is going to be, 15 ppm. That may be absolutely true based on your calculations. You might have done everything perfectly, but it is going to depend on not only the assumptions that you make in the, what you have leeway for solving the problem, but also the accuracy of the Pasquill-Gifford model. So it's important to always say you're assuming Pasquill-Gifford, stating your sources and all that stuff. Point number 4 is that this model only applies to a neutrally buoyant dispersion. So I'm not going to address what happens if it's not. So that this means that the gas is the same density as air. If the gas is heavier than air, for example, that would be obviously a worst case scenario because it would have a harder time vertically mixing. But in contrast, a light gas, like helium would be an example, which is not toxic, but I think you get the point. If it was a toxic gas that is just going to float away, that is not going to be as hazardous. So for that, there are completely different dispersion models, which again, I won't talk about here. I'll just allude to them and point you to the textbook if you're interested. These models, the Pasquill-Gifford model specifically, is only valid up to 10 kilometers from the release point. So beware if you're trying to extrapolate beyond that it may not be accurate. And then lastly, these models are time averaged. So the instantaneous local concentration might exceed the predictions. So if you calculate that the concentration is going to be 15 ppm, you should not be surprised if there's a local concentration that is 20, for example. So again, erring on the side of caution is important and stating all assumptions. Let's now, to finish out this video, look at a quick example problem where there's an accidental release of a neutrally buoyant hazardous gas at a chemical plant in Tampa. The release occurs at the top of a 20-meter stack with a continuous rate of 50 grams per second. Wind is due east at 6 meters per second, and we want to determine the mean concentration on the ground 500 meters downwind. Sorry, this is a mistake. I think this should be, let me check my notes actually. I forgot to copy. It's supposed to be 50 meters crosswind in addition to 500 meters downwind. And then lastly, the location of the maximum concentration on the ground. So let's start by going through the steps. So number 1 is determine our atmospheric stability. We are stated that we are in Tampa. However, it does not say whether it is nighttime or daytime. So in the spirit of assuming the worst case scenario, we will assume that this is nighttime in Tampa. And we also have a 6 meter per second wind due east. So let's scroll up and go over to our table that tells us which class of atmospheric stability we have. We will assume that we are nighttime, and I don't remember if the problem said how great the cloud cover was, but either or, it doesn't necessarily matter. If it is a 6 meters per second wind speed, we're going to be atmospheric stability of D. Tampa is absolutely urban. We also have a plume, so this is the correct table to use for a plume. So for D, we are going to be looking at these dispersion coefficients, so I will copy them below. Okay, so I've copied and pasted my dispersion coefficients, and all I'm going to do is plug in x is equal to 500 meters because that is where we want the downwind concentration. And what I get when I do that is that sigma x is 80 and sigma z is 69.2. Next thing I did is I looked up the dispersion model for my situation that I have, which is a plume, a continuous plume at a release height. However, all three questions are asking me about the ground level concentration. So for that, I'm going to set z equal to 0. And when I do that, this is the simplified form of this equation. Now let's move on to part A. And in part A, all I have to do is plug in x is equal to 500 and y is equal to 0. So let me pause and do the calculation. Sorry, just found a mistake. Sigma x, I did not get 80, I got 73. So let me keep doing my calculations. One more tiny mistake, sigma z, I actually got 65.2. And I decided I actually wanted to take you through my calculations. So at the risk of being boring, hopefully you'll find this interesting and instructive. Let me zoom in for a second. This is Excel. I love to perform calculations on Excel. If you haven't met me before, you probably know this if you've taken MEB with me. But what I like to do is plug in all my parameters. And you see here, I'm using the formula bar to determine what sigma x and sigma z are as a function of x. The reason why I like to do it this way is if I wanted to change the problem in a different way, I could very easily plug in 400 and then sigma x and sigma z are going to automatically update. But anyway, the reason why I wanted to step you through this calculation was because units, again, are going to be super important. So I'm going to keep this column being my meters, or my units. This is in grams per second as specified by the problem. X, Y, and Z are in meters, as is HR, and then the wind velocity is in meters per second. So the first time I did the calculation, I was a little bit surprised by how small the answer was, but you have to think about what your units of that result is going to be. So if I have grams per second on the top, and then I've got meters cubed per second on the bottom, the argument of the exponent term is dimensionless. So I'm going to be left with units of grams per meter cubed. And remember, a very, very small concentration in grams per meter cubed does not necessarily mean it's a very small concentration ppm-wise. So again, in order to do this conversion, I have to know what the molecular weight of toxicant is, but I just wanted to show you order of magnitude wise what it would be. So in this formula, what I've done is I've taken the concentration in grams per meter cubed, and I'm multiplying it by R, multiplying it by T, and I'm assuming the temperature is 300 Kelvin, and dividing by atmospheric pressure and dividing by the molecular weight. So here's where we make the assumption, right? Again, for a toxicant of a different molecular weight, my CPPM is going to be different. And the problem didn't tell me what the molecular weight was, but that is going to impact my answer. So I've just assumed 30 just to give you an idea for what the conversion from grams per meter cubed to ppm would be. So this is my answer for, well, let me get rid of this. This would be my answer for part A. Because this is a very, very small number, what I might suggest doing is multiplying this by 1,000. And when you do that, you convert the concentration into milligrams per meter cubed. And that would be a slightly more acceptable way to report your answer. In the second part, I was asked what the concentration was at x equals 500 meters and y equals 50 meters. So again, the benefit of doing this in Excel, and just to show you my calculation here, I had to check, double check, and triple check this equation. So I encourage you all to pause the video now and do the same. Check, double check, triple check to make sure that this expression is the same as what I've input. But if you take care to make it general, so actually, I'm not taking my own advice here because this is assuming that z is equal to 0. If I wanted to be very proper with this, I would have used the other form of the equation where c is not assumed to be 0, and then we could play with z, the vertical direction as well. But hopefully you'll forgive me. So this is going to be my answer for part B. The concentration 500 meters downwind and 50 meters crosswind is going to be less. And just to show you, if I go back to 0 for y, my concentration goes back increased. Sorry, 50. Now, part C asks me where the maximum concentration was on the ground. And if you look in the book has an equation and a way to do this. But actually, I'm going to do it a slightly different way. I'm going to use goal-seek to figure this out, because one option, what I could do is I could sit here and I could just choose different values for x all day long until I get until I figure out what the maximum is. So this is called the guess and check method. And again, just to point out, the closer I am to the release, I guess I can't be right at the release. The closer I am to the release, the less the concentration is. So let's go back to, or let's go even further away. And we'll see that the concentration actually increases as I get further out. Well, to a limit, I suppose. But we want to figure out where this concentration is maximized. So what I'm going to do is I'm going to use Solver, and I will click on that cell, and I will go to Data, Solver. Now, this is something that you have to add in, and I have YouTube videos on this if you don't know how to do this. But I'm going to use Solver, and I'm going to maximize this cell, because that's what I want to find, the maximum value of concentration, by changing the variable cell of x. That is the only thing that will change. Subject to constraints. I don't have any other constraints, but if I did, I would list them here. I want to uncheck this box and click Solve. And look at that, it gives me 102 meters downwind is where the maximum value is. So I can prove that to myself by trying other values, and I should see if I go either way, then my concentration is going to decrease. The other way I could do this is by plotting it. So just imagine, I'm not going to show you how to do this, but for different values of x, you could calculate different values for sigma x and sigma z and do the calculation multiple times and plot it. I'll probably have you do that on a homework assignment. But that would be how I would figure it out. I think this video has gone on long enough. Thank you for bearing with me through some difficulties and mistakes, and I'll see you next video.